Alright, hey everyone, so good afternoon. Hope your day is going well so far. Today we will be talking about complex zeros of polynomials. Yesterday we talked about complex zeros of quadratics, so today we're going to extend our thinking to, higher powers for polynomials. That being said, let me state the do now. Here we have this polynomial here, x cubed plus x squared plus 81x plus 81, and I want you to find the zeros of this polynomial. And as a hint, I want you to factor by grouping. So, factor the GCF, greatest common factor, from these two terms, and then for the latter two terms, do the same thing, and then finish the problem from there. Okay, I'll give you another minute to do that, and then we will discuss the solution. Okay, does anyone still need the slide here? Otherwise, I'll move on. Okay, so I'm going to jump up to the lesson for the solution. Alright, here it is. Alright, so first thing we're going to do is factor out x squared from both these terms. We have x squared times x plus 1. And then the GCF, the greatest common factor for the latter two terms, is 81, right? So we have 81 times x plus 1 equals 0. And I said equal to 0 because we're finding the zeros. So by definition, right, we want the y value, the output, to be 0. So we're essentially just asking, like, which x values make this function 0. Okay. At that point, you can factor out the GCF here. So both these terms have x plus 1. So it's x squared plus 81 times x plus 1 equals 0. And then by the zero product property, you can set both equal to 0. We get x squared plus 81 equals 0, or x plus 1 equals 0. So we have x squared equals negative 81 after you subtract 81 from both sides. And then for the x plus 1 equals 0, you subtract 1 from both sides. Okay, for this one, we get x squared equals negative 81. And then as we know from yesterday, right, we can take the square root from both sides. We get x equals plus minus 9i, right, because you get square root of negative 81. Take out the negative 1, you get I, and then square root of 81 is 9. So plus minus 9i. And then for the other one, we get x equals negative 1. That's our other 0. Okay, so the zeros in summary, they are 9i, negative 9i, and negative 1. You could also write that as plus minus 9i and negative 1. All in all, though, yeah, that's your final answer. And then as a reminder, 9i and negative 9i are called conjugate pairs, okay, which we'll talk about in this conjugate zeros theorem, which we'll provide the notes for today. But before we get there, just make sure you have this in your notes, and then we will move on. All right, and anyone still need this solution here? Okay, I'm gonna move on then. So just as an overview of the rest of the lesson, we have the conjugate zeros theorem, and then we also have an example that will demonstrate the conjugate zeros theorem, and then after that, it's just a practice question. All right, so let me get to the slide for the theorem. Here it is. All right. This, by the way, is called Z bar, but yeah, can someone read this for us, please? All right, we'll go to Bipra and then Anthony for the next one.
If the polynomial p has real coefficients and if the complex number z is 0 of p, then its complex conjugate z bar is also a 0 of p.
Okay, thank you for that. So we also saw this in the do now, right? We had like 9i and negative 9i, right? So yeah, just be mindful that we're not going to prove this theorem, but yeah, conjugate, whenever you have a complex zero like 9i, the conjugate of that zero, in that case negative 9i, also has to be a zero of that polynomial. Okay, so yeah, just make sure you copy that, and then from there we'll move on to the example. Okay, is anyone still copying the theorem here? All right, now I'll move on. All right, next is this example. So let me scroll up for that solution. All right, so this polynomial is x to the fourth minus 3x cubed plus 7x squared plus 21x minus 26. And this is actually a good example of how I want you to do your homework, right? So first use the rational zeros theorem and also Descartes' rule of signs. Okay, so I'll start off with that. Rational zeros theorem, right? We have plus minus b over q. So the factors of negative 26 is going to be 1, 2, 13, 26. And the factors of the leading coefficient, just 1, so just 1. And then therefore the possible rational zeros for this polynomial, they're going to be plus minus 1, 2, 13, and 26. And then from there we'll use Descartes' rule of signs to find the positive real zeros, or the number of positive and negative real zeros. For the positive real zeros, remember we just need to find the changes in sign. So here there's 1, here there's 2, and then the last one is right there. Okay, which means that there's going to be 3 positive real zeros or 1 positive real zero, right? Because Descartes' rule of sign says that the number of positive real zeros is equal to the number of changes in sign, or is less than that by an even whole number. Okay, so it's 3 or 1. Okay, and then for the negative real zeros, we need to do p of negative x. So p of negative x will be x to the fourth plus 3x cubed plus 7x squared minus 21x minus 26. And for that, we'll have one change in sign here. And yeah, that'll be it. And so we can conclude that there's going to be one negative real zero. Okay, so yeah, again, that's what I want to see on your for your work, on the homework. But yeah, from there, at this point, you could use a calculator. I didn't show like, yeah. So I recommend that you like just plug in the function, like this one, into the calculator, and then you can see like which ones are the actual x-intercepts, right? So first, I did synthetic division, right, for the number 1. And remember, we want to use the coefficients of the original polynomial, p of x. So that will be 1, negative 3, 7, 21, negative 26. And then the synthetic division will yield the bottom row to be 1, -2, 5, 26, 0, which means that 1 is, in fact, an x-intercept or a 0 of p of x, which means we'll have x minus 1 times x cubed minus 2x squared plus 5x plus 26. Okay. And then after that, we have, I showed it for -2, which we can confirm is also a 0. And for that, we're going to use these coefficients, right? We're going to break this quotient down. So we have 1, -2, 5, 26 as the coefficients. And yeah, you'll get the bottom row to be 1, -4, 13, 0, which means since we have a remainder of 0, -2 is a 0 or an x-intercept of the polynomial. Which means we can write this as x minus 1 times x plus 2 times x squared minus 4x plus 13. And then at this point, we're going to use the quadratic formula, which will be -4, which is positive 4 in this case, plus minus square root of b squared, which is 16, minus 4 times 1 times 13, and that'll be 52. Divide that by 2a, so 2 times 1, which is 2. And that will yield 4 plus minus square root of -36. Square root of -36, that's 6i, right? So yeah, if you take out the -1, you get I, and then square root of 36 is 6. So you get 4 plus minus 6i over 2, which will be 2 plus minus 3i. So therefore, with all that being said, we can write this polynomial as x minus 1, right? That was this 0. X plus 2, that was this 0. And then x minus the first complex 0, 2 plus 3i. And then the other 0 is 2 minus 3i. And then the other step I did to write the final answer was just I just distribute the subtraction sign here. So yeah, this becomes x minus 2 minus 3i times x minus 2 plus 3i. All right. Yeah, and also this confirms the conjugate zeros theorem, right? Because as we see, 2 plus 3i is a 0, and 2 minus 3i, the conjugate of 2 plus 3i, is also a 0. Okay, so I'll give you some time to copy that, and then we'll move on to the other question. Okay, does anyone still need to copy this solution here? Okay, not then I'll move on to the classwork. All right, for that, we have about 9 minutes left, so I'll give you some time to work on it on your own. So yeah, do the same thing we did before, right? Rational zeros theorem, Descartes' rule of signs, and then at that point you can use a calculator to check which ones are the x-intercepts for this polynomial here. So I don't expect you to finish this on your own just yet. We'll reconvene at, say, like 3 minutes to use the rational zeros theorem and Descartes' rule of signs. Okay, and then we'll reconvene. All right, 2:35. Okay, so let me pause you here, and hopefully you were able to make use of the rational zeros theorem and Descartes' rule of signs. All right, here's the solution. Okay. All right, Anthony, you were raising your hand before. Are you okay with talking about this rational zeros theorem?
Sure, I guess. Um, the rational zeros theorem, you just divide 25 over 1 and 2. So you get 1, 1/2, 5, 5 over 2, 25, and 25 over 2.
All right, very nice. Yeah, and yeah. So just to elaborate a little more. Numerators the factors of -25, right? The constant term, and then q, those are the factors of 1 and 2, right? So we get these numbers as our possible rational zeros. Okay. And anyone for Descartes' rule of signs? So the answer is 1 positive real 0 and then 3 or 1 negative real zeros. But how do we know that? All right, what offer?
So we can determine that it's one positive real zero by looking at the changes in signs of p of x, and we see that there's only one change from positive 2x to the fourth to negative 7x to the third. And then if we substitute, or if we plug in negative x to solve for the negative real zeros, we see that there are three sign changes, but we also, so that means there's either three or one negative real zero, because we can also subtract one whole even number, and so 3 minus 2 is 1, so you have either 3 or 1 negative.
All right, very nice. Thank you for that. So yeah, we have 1 positive real 0 and then 3 or 1 negative real zeros. Okay, so again, Descartes' rule of signs is conclusive, right? This tells you like there are, but rational zeros theorem, these are possible rational zeros. Okay. Anyways, I'm gonna plug in 5 for a 0, and we can confirm using synthetic division that it is an x-intercept or a 0 of this polynomial. So we get 2, 3, 11, 5, 0 for our bottom row, which means that the polynomial can be written as x minus 5 times 2x cubed plus 3x squared plus 11x plus 5. Right, remainder 0. So yeah, just that tells us that it is a 0. And then from there, I'm going to factor this further, right? 2x cubed plus 3x squared plus 11x plus 5. I'm going to divide this by x plus 1/2, which means that the c value is -1/2. So the coefficients there are 2, 3, 11, 5. Okay, and then you can see from the bottom row, it's going to get, sorry for the misplacement, but yeah, we get, 2, and then 2 after you add, and then 10 and 0. Which means that the polynomial can be now written as x minus 5 times x plus 1/2 times 2x squared plus 2x plus 10. Okay, so at that point, you can use the quadratic formula. Before I did that, though, I factored out a 2 from this. Up to you, though, you can just directly use the quadratic formula for this. So yeah, here I write, apply the quadratic formula for x squared plus x plus 5, and you get negative b, which is -1, plus minus square root of b squared, which is 1 squared, minus 4 times 1 times 5. 4 times 1 times 5 is 20, so you get 1 minus 20, and then divide that by 2a, which is 2 times 1 in this case. Okay, so that'll simplify to -1 plus minus I root 19, right? Because you have a negative 19 on the radical, divide that by 2, and then I divide both numbers by 2 to write it in a plus minus bi form. Okay, this means that our polynomial can now be written as x minus 5 times x plus 1/2, right? Those are the original two. And then this, 2 times x squared plus x plus 5, right? Here I had the 2, but the x squared plus x plus 5, that could be broken down as we saw, right? Using these two zeros. So it's x minus the first 0 of -1/2 plus I root 19 over 2. And then the other 0 is -1/2 minus I root 19 over 2. And I guess technically I should write this as, put the I there, right? A plus bi form. Not a big deal though, like mathematicians will know what you're talking about if you write it like that. Yeah, just to be consistent with the textbook, or like that. Okay. Yeah, and then after that, for the final answer, I just associated this 2 with the x plus 1 half. So I did 2 times x plus 1 half. You get 2x plus 1. Looks nicer, like no fraction. And then after that, I distribute the subtraction sign. So you get x plus 1 half minus 19 minus root 19 over 2I. And then x plus 1 half plus root 19 over 2I. Okay, and that'll be your final answer for this question. All right. Scroll up a little bit. All right, but yeah, that was the solution to this. And all right, let me close with announcements while you finish copying. So one, there's SGI today per usual, 247. Secondly, if you want me to grade anything manually for quiz 7, please leave a private comment on Google Classroom, letting me know which question you want me to grade, and tell me, like which page, if you submitted multiple pictures, which page the work is on for which problem. The other thing is tomorrow's a half day, so we have a different schedule. We are meeting though. We have this is eighth period, so but the time is now shifted to like I think it's like 10:50 or something. I'll post the schedule on Google Classroom for your convenience though. But yeah, we'll meet tomorrow in the morning. But okay. All right, but yeah, if you're done copying this and you have no further questions, you're free to go, and I will see you all tomorrow.
Bye, thank you.
Bye, thank you. Have a good day.
Thank you, you too.